Hey everybody, thanks for tuning in here. We're going to take a look in this video at something called the vertex form of a quadratic function. All right, you've been studying quadratic functions for a while and you are no doubt familiar with something called factored form, written like that, where you see the parabola or the quadratic function written out as a product of factors and you get the two x-intercepts right there presented in the equation to you. That's very nice. You're also familiar with the standard form. In this form, you get the y-intercept, and that's also very useful. Okay, but in neither one of these forms do you get another critically important point on any quadratic function, which is its maximum or minimum point, the vertex. And so the vertex form looks a little bit different here. Y equals a times x minus h squared plus k. All right, and in the vertex form, as the name probably suggests to you, you do see the coordinates of the vertex just presented right there directly in the equation. You don't have to dig around or do any calculations. They're just right there. So that's really nice. Let me make a comment here about these letters that we choose. It's not really arbitrary to say A, B, and C, and H, and K, and M, and N, and all that stuff. Notice what's the same about all of them. All of them use the value A in all three forms, and that's for a reason. That's because that A value, whatever number that is, that will stay constant in all three forms. In other words, if you started with a factored form of a quadratic function and you multiplied it all out to get standard form, that A value there would be the same number in both forms. And furthermore, if you converted standard form into vertex form, which is what I'm going to show you pretty soon, that same A value will be there. So that is, it's correct that it should be the same letter in all three forms. We have different letters for the x-intercepts, A, B, and C there in our standard form, and the H and K give you something completely different. So we should use different letters for them. All right, well, let's take a look then at this process that I was just talking about of converting a standard form to a vertex form for a quadratic function. All right. The process that we will use is something that you are somewhat familiar with, I hope, completing the square. All right, and so in this process of changing standard form to vertex form, what I'd like to do is do a couple of examples where A equals 1 and one example where A does not equal 1. And if you recall any work that you have done with completing the square for solving quadratic equations, you do have to take that A value into consideration. If it's positive 1, you have a kind of a nice, easy process. If it's not positive 1, well, you have to do some other extra stuff. And that's true in this process also. Okay, so we'll do one example of each. First one we'll take a look at is an example where A equals 1, x squared minus 8x plus 3. And as you might remember, what we're going to do first when we complete the square is just move the constant over to the other side. So that looks like that. Y minus 3 equals x squared minus 8x. And the next thing that we do is we add that special number there, b over 2 squared, to both sides. In this case, b is negative 8, and negative 8 divided by 2 is negative 4, and negative 4 squared is 16, so we are going to add 16 to both sides of that equation. Well, after this, if you recall the process of completing the square, all we need to do next is factor the right side into a perfect square binomial, and we'll just simplify the equation. That factoring process is really pretty simple in the completing the square process. It always kind of works out to be the same way. So your final equation there kind of looks like this, and then simplifies down to y equals x minus 4 squared minus 13. So that's what we call vertex form. All right, and the vertex of this parabola, if you go back and look at the first slide we did showing the vertex form, the vertex of this parabola is positive 4, negative 13. Please notice that the x-coordinate, the number inside the parentheses with x in the equation, that number, you could say that it changes sign when it's not strictly that's what's happening, but it looks that way. So if you see x minus 4, then the x-coordinate of the vertex is positive 4. Okay? On the outside, though, the y-coordinate is the same, so minus 13 means negative 13 for the vertex. All right, so pay attention to those little details right there. And let's try another one now where a does not equal positive 1, and I've chosen y equals 3x squared plus 12x minus 7. All right, so first step is going to be the same. We're going to move the constant over. All right, so we'll add 7 to both sides. And now, if you do remember this, anyway, or if you don't, this is what we had to do. We have to factor out that a value on the right side there. All right, factor it out. We're not going to divide everything by 3 because we want to keep the 3 in the equation. We don't want to lose it. So we're just going to factor it out, and you can see I'm leaving a little space there to add our special little completing the square number. But we've got now 3 times the quantity x squared plus 4x. All right, so that's what happens when you factor out a there. You're dividing both of those terms by a. Keep it there in the parentheses. All right, now, so what we'll do is we'll add the b over 2 squared, which turns out to be a positive 4. On the right side there, we add that inside the parentheses, b over 2 squared. But keep in mind that what we are doing now, even though I added 4, that 4 is being multiplied by that 3. So it looks like I wrote a 4, but we're actually adding 12 on the right side of the equation. So that's what we have to add on the left side to keep the equation balanced. All right, so after this, it's pretty much the same process. You're going to factor out that right side into a perfect square binomial, simplify the equation, and there you go. Y equals 3 times x plus 2 squared minus 19, and the vertex is at -2, -19. All right, once again there you see that switch of the sign there for the x coordinate of the vertex. Okay, well, I wanted to make another comment here because we use our book that we use has one kind of terminology, but a lot of other books may use different terms here. And so to make this a little bit more useful for more people, I wanted to make this comment here that sometimes vertex form is called graphing form. It's not very common, but you do occasionally see books that use that phrase instead of vertex form. Most people use vertex form because of you get the vertex in the equation. But the graphing form, calling it that, is not a bad choice. Let me explain why. It emphasizes a slightly different aspect of writing equations in this form and their kind of transformational nature. Let me explain what I mean by that. Let's say you've got a parabola x minus 3 squared minus 5, and that vertex there is at positive 3, -5. Okay, well, we can think of that as that's the equation of a parabola, but let's think of it in a slightly different way. If we think of a parabola that has not been moved around at all, in other words, just a plain old y equals x squared parabola, like that, x minus 3 inside the parentheses there means that the graph has been shifted to the right 3 units. That's what x minus 3 does. It shifts the graph to the right. It's a little counterintuitive to say minus means go to the right. I understand that, but that's something you just have to get used to, I guess. And the -5 on the outside means that it has been shifted down 5 units. So writing the equation x minus 3 squared minus 5 is almost describing 2 transformations, a horizontal shift of 3 units to the right and a vertical shift down 5 units. So that's what I mean. This graphing form, it's a useful way of thinking about it. It's sort of like a different little aspect of this process. Let's do one more, all right, just to kind of emphasize that. Let's pick one like this. It's -2 times x plus 1 squared plus 4, all right? Well, that -2 means that the parabola opens downwards because of the negative sign, and the 2 means that it is twice as steep. That 2 is kind of like a scale factor on the parabola. It makes it twice as steep. The +1 inside the parentheses there means that it is shifted left 1 unit, and the +4 on the outside of the parentheses means that it is shifted up 4 units. So you can just, with thinking about all of that stuff in the equation there, you can pretty much visualize what this parabola looks like. There's our vertex there at 1, 4, and it's upside down and it's kind of skinny, and that's what it looks like. So this graphing form, calling it that, is I think it's a good description. It's a little non-standard. Most people will say vertex form, but I think the graphing form and this illustrating this transformational process of moving a parabola around horizontally or vertically. I think that's a useful way of looking at it as well. Anyway, I hope you enjoyed that. I hope you got something out of it. I know that was kind of a long video, 10 minutes. It's a little bit much, but I hope you're doing well. And once more, thanks again for tuning in. See you soon.